Welcome to the CompTIA A+, 220, 1101, or Core 1 exam. This is Objective 3.2, Memory Technologies. Let's start our conversation about memory technologies with what we do when we run out of memory. There are ways to help when you run low on random access memory. And one of those things you can do is take information you're not currently using in RAM and swap it out to a hard drive or solid state drive. We sometimes refer to this as virtual memory, although we can also refer to it as virtual RAM or a swap file in Linux. In Windows, in the performance options, there's an advanced tab that allows you to configure a virtual memory section. This is an area of your hard drive or solid state drive that Windows can use as it was actual memory. Obviously, a hard drive or solid state drive is slower than actual random access memory. So this is really an area where we temporarily are storing things until we find more room within our normal random access memory. Many operating systems will manage this process automatically. In Windows, there's a checkbox that says automatically manage paging the size for all drives. But you can manage this yourself. You can uncheck that option and you can specify exactly how much virtual memory you'd like to allocate on your storage device. Another memory technology that can greatly increase the throughput in your system is multi-channel memory. Sometimes you'll see this as dual channel, triple channel, or quad channel memory. This takes the throughput that normally would be sent to one single memory module and spreads that load across multiple memory modules. Ideally, you would have exactly the same memory module type in each of these multi-channel slots. If your motherboard supports multi-channel memory, then you might want to look at the memory modules and see if they have different colors. This is often done so that you know exactly which slot to use for the multi-channel memory. One thing you might have to consider is what might happen to your system if there happens to be an error within the memory that you're using. In some environments, you're able to have memory check itself, and if a memory error does occur, then we can choose to perform some other function. This is a type of memory that you might have in a system that's running virtual machines. Or it may be a very large database server, or anything where you want to maintain the uptime and availability of those services to be as close to perfect as possible. One type of memory you might use is called a parity memory. This adds an additional parity bit to the information that you're storing in the RAM. This isn't a perfect way to identify problems because parity memory can't always identify when an error has occurred. And parity memory has no method to be able to correct any problems that happens to find. Let's see how this parity bit is calculated and added to the existing data. Let's look at this first line of data. And if we want to count the number of ones, so in this particular data, there's 1, 1, 1, 0, 0, 1, 1, 1. You can see it in the first column here. In the first row. We have 1, 2, 3, 4, 5, 6 ones within that data. The 6 is already an even number, so we don't need an additional ones to make this even. Therefore, the parity will be 0. Let's take the next bit of data down on the next row. This data is 0, 0, 0, 0, 0, 0, 1, 0. If we count the number of ones, there is a single one, which means there's an odd number of ones. To be able to make this even parity, we need to add one more into the mix so that we have an even number of ones in this data. And lastly, on the next row, we have 1, 0, 0, 1, 1, 0, 0, 0. We count the number of ones and there's 1, 2, 3 ones. That's an odd number. So we're going to get an even parity then. And now we have an even number on the ones in that data. Let's take a look at the next slide and you'll see what I'm talking about. So within that parity bit, we can run some tests and see if the data that already using appears to be correct. So let's evaluate the parity bit. Assuming that we're using even parity, we'll take the first data and count the number of ones. We have 0, 0, 0, 0, 0, 1, 1, 1, 1. With a 1 as the parity bit, if we continue the numbers of ones, we have 4 ones. This is an even number. Therefore, that data has been validated. Let's do this next bit of data, which is 0, 0, 0, 0, 0, 1, 0, with the 0 on the end. We count the number of ones. That one is an odd number, which means something has gone wrong with that data, and it does not validate. And then lastly, we have 0, 1, 1, 0, 0, 1, 0, 0 with the 1 parity bit. If we continue the number of ones, there's 1, 2, 3, 4 ones, which means it's an even parity. That validates and that data appears to be correct. This is how the error correction works on the memory module. Well, we're at the end of the objective. Here's a real-life question. On which of the following systems would you find error-correcting memory modules? In a home computer, in an office computer, in a small office, home office print server, or in a Swift banking routing financial system? Well, obviously, the most important of these systems would be a Swift or a routing system. You absolutely cannot make errors when you're moving monies from bank or doing some online banking yourself. Imagine what a crazy world it would be if you didn't get that deposit or if your money didn't come through from your paycheck. Thanks for watching.